So yesterday we took some time to play a game and gather experimental data of two dice sums and figure out what is the best strategy for playing counters game. And we learned that when we roll a pair of dice 50 times that the number 7 appears the most often. And so that's experimental data when we gather the data and look at that. Um, Today we're going to look at, all right, theoretically what should happen. So we took a look at the class data. This is what we saw happen, but what should happen? So experimental data is, again, the data that you collect and analyze. Theoretical data is what should happen. So let's look at the theory of playing counters game when you roll two dice and add the sums together. Which numbers should pop up the most often? And so this is called an area model, where we're going to put all the results from the first event, 1, 2, 3, 4, 5, 6 are the numbers that we can roll on the first dice, and then same thing on the side, it's the numbers that we can roll on the second dice, and we're going to add those together. So if we get a 1 and a 1, then our sum will be 2. If we get a 2 and a 1, our sum will be 3. 3 plus 1 is 4, and so on. So we'll just fill this out. Here, 2 plus 2 is 4. We have some 5s here, 6s, 7s, 8s, 9s, 10s, 11s, and 12s. So if you think back to playing counters game, did you see a 2, or when we looked at our theoretical data, did you see a 2 happen a lot? And the answer is no, we didn't see 2s very often. We didn't see 12s very often, and here's why. So theoretically, when you roll two dice together, there's only one way to get a 2, and there's only one way to get a 12. And so that's why we didn't see those numbers pop up very often. And theoretically, we should see a 2 happen 1 out of, and the total here is there's 36 options. And so that percentage is really small. If we take 1 divided by 36, the probability of rolling a 2 or a 12 is about almost 3% every time. And so we can use this, and this is the theoretical data, what should happen, what are all the outcomes that can happen when you roll two dice together. Probability is the extent to which an event is likely to occur. It's measured by the ratio of favorable cases to the number of whole number cases. So put measured right there. So the probability notation, the probability, you'll see P for probability of an event happening. So event A is the number of times A happens over the total number of events, or total number of outcomes. So there's probability. So let's do some examples of this. Experimental data, again, is data produced by trials and observations. Our experimental data was rolling the dice 50 times and then recording our class data. Experimental probability is what actually happens. So for example, let's say the probability of rolling a 7 out of 100 times was, I don't know, we'll say 67 out of 100. So I'm just making these numbers up, but we'll have our actual class data to look at. If that was the case, again, 67 would be the number of times you roll the 7 out of 100 times total. You can write probability as a fraction, a decimal, or a percent. As a decimal, we'll divide 67 divided by 100. That's 0.67. We can multiply that by 100 to get the percentage. So if this was our data, it would indicate that there was a 67% chance of rolling a 7. But what should have actually happened? The theoretical data, or theoretical probability is what we should expect to happen. And so if we take a look at this, we can count how many 7s there are. 1, 2, 3, 4, 5, 6. Right, so there's 6 7s out of 36 total outcomes. So again, if we count all the boxes, there's 36 there. So then we can do 6 divided by 36, and that is 0.167, repeating. As a decimal, so it's about, I should put wavy lines here, 16.7, I'll put 8% of actually rolling a 7. So I guess the 67 I put here was too high. All right, so theoretical data is what should happen, and experimental data is what actually does happen when we do the experiment. So think about the differences between these two. What should happen and what will happen as you play our next game. It's called Odds or Evens. Who will win? All right, we're going to play a game. You and your partner must decide who will be odds and who will be evens. Then you will roll 2 dice and you're going to multiply the numbers this time. If the product is odd, the odd person wins, and vice versa for evens. So if you roll the dice and multiply them and you get an even number, the even person wins. Play the game 20 times and keep track of the results. Okay, so how many times does the odd person win? How many times does the even? Together, your tally should be 20 people. All right, so I'll just do an example here again. Our experimental data in class will be different. How many times does the odds person win? So it should be some number out of 20. So we'll say 6. Maybe they won 6 times. Right, this is a fraction out of 20 and turn it to a percent. So 6 out of 20. Let's get the decimal for that. That's 0.3 and multiply by 100 to get 30% chance of winning. Here we go. Record your result on the whiteboard. Find the total percent of rolls that were odd products. We're just going to count how many odds were there out of the whole class. So again, an example, let's say there were 78 odds out of 300 results. Find the total percent of rolls that were odd products for the whole class. So again, we can divide. We can get 0.26, which is 26%. Can we say that the percent from the whole class is the true probability? And we would say no. This is the experimental probability. All right, and to get the actual probability, you would have to keep playing the game forever to get the true probability. Number 4, to determine the true probability of rolling, we would have to look at the theoretical data. And so the theoretical data will use another area model where we put what can happen the first roll and what can happen the second roll. One will put horizontally, one will put vertically. And this time we're going to find the products where we multiply them together. And then we're going to circle all the products that are odd. Okay, so 1 times 1 is 1, 1 times 2 is 2, so we're just multiplying. And then we're going to multiply everything by 2. Multiply everything by 3. And so on. So let's circle all the ones that are odd, because that's what the probability that we're calculating. None of these are odd. These are odd. None of these are odd. These are odd. Okay. So it says use your table to find the probability of rolling an odd product. Okay, so if we count those, that is 9 ways out of, again, there's 36 total outcomes here, which is 1/4, 0.25, or 25%. So this is the theoretical probability of rolling an odd 25%. Ooh, that's pretty close to what we had for the class, which was 26%. Use the table to find the theoretical probability of rolling each of the following products. So when they want probability, they might put a P in front of it. So what's the probability of rolling a 12? And how many 12s are there? We would have to count total 12s. 1, 2, 3, 4. 4 out of 36. And again, we can change that to a decimal or percent. I kind of like percentages, so that's about 11.1% of rolling a 12. Okay, how about rolling a 15? So again, we should put probability of rolling a 15. And we count the number of 15s. All right, so here's a 15, and here's a 15. So, ooh, even smaller, 2 out of 36. Again, I like the decimal or the percent, so I'll divide it out and change it. So it's about 6%. And so on. How about a 12 or a 15? So you're going to count the 12s and the 15s, or we could just add these together, right? Yeah. So there's 4 12s, there's 2 15s, so one or the other. There's 6 of them out of 36, which is a 1/6 chance, which is about 17%. What's the probability of getting a 25? I think there was only one 25 here. So, 1 out of 36, a very low percent chance of getting that 25. About 3%. What's the probability of getting not a 25? All right, so one way we could do it was we could count everything that's not 25. But we know that there's 36 total, and one of them was a 25. So if we do 36 minus the 125, we have 35 ways to get not a 25. So that should be about, what, 97%? Because 100 minus 3%, but we can calculate it more accurately here. Yeah, it's about 97%, 97.2. And then what's the probability we get between a 1 and a 36? And all of these numbers are between 1 and 36. So 36 out of 36 is 1, or 100% chance that you will get between a 1 and a 36. All right, let's check for understanding. What is your favorite color Skittle? Based on a very large sample, so this would be experimental data here, here's the distribution of color for Skittles that come in fun-sized bags. All right. Ooh, and mine is red. And notice we don't have the result for red. How could we calculate that? Well, we know that our probability has to add to 1. And so if we add up all, all the other probabilities and subtract from 1, we should get the red. So let's do 1 minus each of these probabilities. Okay, so I'm just subtracting all of these to get red. So 1 minus 0.171 plus 0.214 plus 0.204 plus 0.214, and that is 0.197. So we only have a 19.7% chance of getting my favorite color, a Skittle, which is red. Oh, and we actually answer this question right here. Find the probability for getting a red. Oh, and I didn't read the question. It says, explain what the probability of getting a purple of this right here means in the setting. Okay, so I should answer that. I was just reading this question right here. What's your favorite color Skittle? All right, so this means you have a 21.4% chance of getting purple in a fun-size bag. And the more Skittle bags that you eat, the more close to this percentage your chance will be. What is the probability that a randomly selected Skittle is green or purple? So we can add those together. We know purple is 0.214, green is 0.214. Nope, that was purple. Green is 0.171. So the probability of green or purple is 0.385 or 38.5%. What is the probability that a randomly selected Skittle is not yellow? Okay, so if you take a look at yellow, an easier way to do that is called to find the complement, just subtract. We know that this should add up to 100%. So if we do 1 minus the probability of getting a yellow, we should get the probability of not yellow. And if we subtract that out, it is 0.786. You have a 78.6% chance of not getting a yellow. All right, so your assignment today then is to hop onto Schoology. There's a link that will take you to this Desmos simple probability and finish that for tomorrow.